Griffith does this better than anybody else, I think, and so we're going to follow him very closely. What he does is he starts us off with discrete probabilities, and then ushers us into continuous probability.
They didn't do any of this stuff in my nursing statistics 101.
No solving for wave functions? You might do it here as well. You might do this stuff. Okay, so let's start off with discrete. All right, and so I'm going to follow the example in the book. I forget what these are, but Griffiths gives some type of you have some type of data. All right. For example, I forget what the example
number
was.
of people per age in a room.
Okay, so there's a room, and there's one person at the age 14. There's 3 people at the age 16. There's 2 people at the age 22. There's 2 people at the age 24, and there's 5 people at the age 25. All right. So the first thing to do is from your data, create a histogram. And down here in the histogram, the ages, and there's 14, 15, 16, 17, 18, 19, 20, 21, 22. I'm going to zing through this as fast as I can without doing all my sidebars. All right, 24, 25. All right, so at 14, there's 1. At 16, there are 3. All right, at 22, there are 2. So 2, at 23, at 24, there are 2. And then at 25, there are 5.
And then 1 and 15.
Okay, thank you. 1 at 15. 1 at 15. Okay, so I have a histogram of data. These are number of hits. Yes, why not? Number of hits. There's 1 hit here, 1 hit here. How do I change my histogram to a probability? How do I go from an outright histogram of numbers to a probability distribution?
You need to know the total number of people.
Okay. So in essence, what I'll do is I'll say probability is by n total. So probability. So this will be like 1 over, how many altogether are there? 14?
14.
1 over 14, 3 over 14, 2 over 14, 2 over 14, and then 5 over 14. Okay, so what I'll do is I'll call this like P sub I. So P sub I, for example, P sub 14 equals 1/4, 1 over 14. And then P sub 15 equals 1 over 14. And P sub 16 equals 3 over 14. Okay? So those are the discrete probabilities. And what do I know about the following? If I go the summation over I of P sub I, what does this equal?
1.
It has to equal 1. Alright? By very definition.
You'll get some answer.
What's that?
Because you're going to get some answer.
But I'm going to get some answer. I'm not trying to...
No, because you're going to get equals 1, because you're going to get something.
Yeah. The probability has to add up to 1. Right. Yeah. Now, let me just foreshadow a little bit. So this is an idea that links us to kind of the discrete case. I could have defined rho as a probability per unit bin size. All right? And if I had that, then I could have said, let's see, then P sub I would have equaled rho sub rho times a bin. All right? And you can see right here is what I'm saying is the probability depends upon the size of my bin. Like here I said let the bin be 1 year apart. Right? What if I said let the years be 2 years apart? Then how many people would I have in that bin? 2, and so on. So very definitely the probability depends upon your bin size. All right. So over here, if I had a function probability per unit bin, I would say that the probability is that this probability density times the bin, and that would equal probability per unit bin times bin, and those cancel. All right, so what I'm doing is I have a unit bin size. All right, it's probability per unit bin. All right, but now that we have the probabilities, we can ask a question. What is the average age? Now, with probabilities, P sub I, compute stuff. Okay, and the first question is the following. What is the average age? Okay, so you've noticed that I've used these letters, these symbols, the cat. All right, and that will come on to, whenever you see that, that will mean the average. All right, now, this also equals, if you want, age. All right, with a bar over the top, that's another common designation of average. All right, and then another name for average is called the mean, right?
Yep.
All right, so I'm going to call it the average, or the mean. All right, and then later in quantum mechanics, we're going to, so this is the average, the mean, or in quantum mechanics, we're going to call it the expectation value. So all of these things are under here. They all have the same.
As was once said, expectation value is what you will get if you had an infinite number of identically prepared states and an ensemble of particles. The expectation value would be the most probable outcome of the system.
Yeah.
Right, that was what you said.
Yep. Yeah. I haven't said it yet, but I've said it before.
Yeah.
Yeah.
Well said.
All right, so let's talk about this discrete case. So let's calculate the average age. How do you compute the average age given this probability?
Yep, you take each age, multiply by its probability, and then you add it together.
Yeah, and
Divide by the number of...
the total number. Yeah, so over here it's something like 1 times 14 plus 1 times 15. I'm not going to do it all. Plus blah, 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 blah. And then you all divide by, what is it?
It's 14.
All right, but let's rewrite that. I'm dividing everything by 14. This is n total. So what I'm really doing here is, check it out. 1 over 14 there, 1 over 14 here, and then the next one, the last one will be 5 times 25. And over here I have 5 over 14.
Even probability.
So I can rewrite this as equal to the summation over I of pi, right?
Divided by n, I to the n, I to n, summation from I to n, and then divide pi by n.
Yeah, we're summing over I, and then, we'll call this I times I, where I is the age.
Yeah.
Okay? Okay. Great. And that works. Does that work?
Yep.
Okay, great. Let me ask a silly question. What is the average of the age squared? The ages squared.
You can just do the same summation, but just do I squared.
Okay, yeah, so it comes out the same. It's kind of 1 squared.
No, it'd be 14 squared.
14 squared, yes. So 1 times
14 squared.
14 squared. Thank you.
1 times
Plus
15.
1 times 15 squared. Plus, so 5 times 25 squared. All divided by 14. So that equals the summation over I of
P sub I squared.
P sub I times I squared. Okay, so here's the scoop. Is that this is in general true. The expectation value of the average value as some function of I is equal to the summation over I of what? Here the function of I was just I, and here the function of I was I squared. Right?
So summation over I of P sub I times Fi.
Yeah, that's it. P sub I times F of I, whatever Fi is. Okay, and so that's a very general result. All right, for discrete probabilities. Okay, the last thing that I want to talk about here is the following. For discrete probabilities, there's another statistical bit of information that we use, and it doesn't fit so well with this, but let's say that I had discrete data. Well, I mean, it's going to apply there, but it's not as nice picture. Let's say that I had data like this. If I had discrete data like that, right? That in statistics, what we do is we kind of, if we have random error, if we assume random error, and we can imagine doing this experiment to infinity. So we were able to do this experiment an infinite number of times. And by doing it an infinite number of times, we were able to take our little bins and reduce the bins down to getting smaller and smaller and smaller and smaller. That if we had truly random error, that data would approach a Gaussian. Right? So if this were I, this shape, this Gaussian shape goes like e to the minus I minus I average squared all divided by 2 sigma. Okay, the shape goes like that. That's a Gaussian. Everybody okay with that?
I minus I squared.
I minus I average. Sorry, I average. Or let me do it with my new notation. I minus I. Okay, that's a Gaussian line shape. Try it on a computer if you want. Go x minus x average. Pick an x average. Go ahead and do it, all right? That's how you're going to convince yourself if you can write it and create it yourself. So try this for homework. All right, plot e to the minus x minus 3 quantity squared all divided by, I think this is a squared, let me see. Yeah, that has to be squared.
Is it? Oh.
Yeah, because this is going to have units of like length squared, so that has to have units of length squared. So I'm pretty sure it's a square. All divided by 2 times, say, 1 squared. And what you see is this number is where the Gaussian is centered. Right? Is that your steps? What? I'm pretty sure it's square. So this is, and I just did a unit check, right? An exponential,
Yeah.
What are the units of the exponential?
Doesn't have any.
It has to be unitless, right? And so this is x minus x bar, right? That's going to have units of x. Right? So x squared, so this has units of x then.
What's the denominator? Yeah.
2 times 1 squared. Play around. Make your own function. Do it yourself. Play around so you learn.
Up there, wait, where you wrote, is it denominator 2 sigma squared?
2 sigma squared, yeah.
What do you want to do? You want to graph that?
Yeah, plot this in Excel or something.
What is I then? Your data points?
Yeah, here it's your age.
It's not,
Right.
it's not square root of negative 1.
What's that?
You're saying it's
Oh,
not
it's
I.
not. No, it's not complex number. Thank you.
All right.
It's, I'm staying with that function over there. Right? Yeah, I mean, look, I guess I didn't write this. That's the average age. This is the average age squared. So I should have written it down before.
And that's different from I in parentheses with the square term on the outside. That's the standard deviation.
Yeah, sigma is the standard deviation. Okay.
Yeah, sigma is the square root of.
Sigma is the standard. So look, this is statistical. So if you have a Gaussian curve, all right, due to random errors, you can show that the standard deviation, this distance right here, that's 68% or 2/3 of the data is within